So we'll come back to this equation in just a little bit. But first I want to actually use this equation to derive this thing called reciprocity. And the way you do that is you imagine the situation where surface I and surface J are at the same temperature. So Ti and Tj are both at some temperature, and that temperature is the same. Well, we know from thermodynamics that heat transfer between two things at the same temperature has to be zero, right? Heat is always transferred from hot to cold. If two things are at the same temperature, the net heat transfer from the one thing to the other thing has to be equal to zero. So in this limit, Q dot I to J, this thing has to be zero. So let's make this substitution. First of all, Ti and Tj are the same, so they'll just be T. And second of all, Q dot I to J has to be equal to zero. So that's what I get, right? This has to be true. And if I cancel out sigma T to the fourth from this, I get that AI times Fij has to be equal to Aj times Fji. This is reciprocity, this equation right here. It's really handy. It says that if I have two surfaces, all I got to do is get the view factor from one surface to the other, and the view factor from the other surface to the first surface comes for free with reciprocity, right? The other thing that I need to emphasize here is, we derived reciprocity in this limit where we have two black surfaces and they're at the same temperature, right? And that's what gave us this equation. But if I look at this equation for reciprocity, there is nothing in this equation that cares that I have black surfaces or that they're at the same temperature, right? If I have two surfaces and they're the same two surfaces, right, in terms of geometry, but they're not black anymore, so I paint them with some reflective coating, and they're not at the same temperature, so I heat this guy up more than I heat this guy up, nothing in this equation changes, right? They still have the same areas, and they still have the same view factors, because this is all a geometric set of equations here. So all these geometric quantities don't change, even if the temperatures aren't the same or the surfaces aren't black. And the point then is that reciprocity certainly works for two black surfaces at the same temperature. It also works for two non-black surfaces at different temperatures, right? It doesn't matter what the temperatures are or what the surface characteristics are. Okay, so that's reciprocity, and that's the other super useful view factor rule. And actually, if I take reciprocity and I go back up here and look at my equation that tells me what's the net rate of heat transfer from I to J, I actually can simplify it, right? Because you can see Fij times Ai and Fji times Aj, that's the same thing according to reciprocity, right? So I can pull them out, and I get that Q dot from I to J is Ai Fij times sigma Ti to the fourth minus Tj to the fourth, right? Or if I want to write it in terms of blackbody emissive power, it's EBI minus EBJ. So here's my equation that I can use when I have black surfaces to calculate the net rate of heat transfer from any one black surface to any other black surface, right? This is my fundamental equation. And actually, it's pretty interesting to look at. If you look at it, it says that the heat transfer rate is driven by a difference in potential, and then there's a resistance, right? So this looks like a resistance equation. All throughout the class so far, when we've had these resistance equations, the potential that drives the heat transfer rate has always been temperature, right? For conduction resistances or convection resistances and on, it's been temperature. When you get these radiation problems, it's not temperature anymore, right? In fact, it's more like temperature to the fourth. Or if you look over here, the potential that's driving the heat transfer is actually the blackbody emissive power difference between the two surfaces. So if I want to represent this as a resistance equation, here's my resistance, right? I have a surface I, it's got some potential EBI, right? I have a surface J, it's got some potential EBJ. The resistance to radiation heat transfer between those two surfaces is Rij, where Rij must be equal to what? 1 over Ai Fij, right? 1 over this quantity here. Or by reciprocity, that would have to be equal to 1 over Aj Fji. So this is this surface-to-surface resistance, right? This is called space resistance. Depending on what book you pick up, it's called different things. But it's basically the resistance to radiation heat transfer between one surface and another surface, right? And I can now start to think about representing my black body problems as just a bunch of resistors that are strung between my different surfaces, right? Yeah, so it looks kind of like this. If I think about this resistance, it makes a little bit of sense. I guess just from a unit standpoint, this must have units of 1 over meter squared, but that makes sense given the units of my numerator are watts per meter squared. So watts per meter squared divided by 1 over meter squared, sure, I get heat transfer in watts, right? The other thing to look at here is, when does my resistor get big? When does it get small? Well, my resistance gets really large, so it makes it hard to transfer energy between these two surfaces when the area gets small. That makes sense. Or when the view factor gets small, right? When the two surfaces don't see each other very well. On the flip side, it becomes very easy to transfer radiation between two surfaces if they have large area or if they see each other really well, so if the view factor becomes large. So I can start thinking about taking surfaces like this. So here's an enclosure. There are 3 surfaces, right? I can represent each surface as a node. Surface 1 is this node, 2 is this node, 3 is this node. And if these surfaces exchange radiation, then there needs to be a resistance between these surfaces, right? So surface 1 exchanges radiation with surface 2. Here's the resistance R12, and so on and so forth, right? And then each node has some boundary condition, right? So there's a radiation heat transfer to surface 1. This would be Q dot 1. This would be the net radiation heat transfer leaving surface 1 and going off and hitting the other surfaces. Same thing for Q dot 2, same thing for Q dot 3. So this is kind of our visual way of dealing with surfaces, with black body radiation heat transfer problems. I guess it should be pretty obvious that if I have more than 3 surfaces, this network idea becomes hopelessly complicated in the sense of drawing a resistance network with 4, 5, 6 surfaces it becomes spaghetti, right? And one of the reasons is because in a radiation problem, it's typically the case that every surface can see every other surface. So when I'm sitting here at surface 1, I have to draw a resistance between surface 1 and every other surface that it can see. It's not like a conduction problem where surface 1 can maybe only see the things that are immediately to the left and the right of it, right? That becomes a nice series resistance network. In radiation, that's not true, right? In radiation, you end up with this spaghetti of resistances that go everywhere. So if I have more than 3 surfaces, I need an easy way to quickly come up with the set of equations that have to be solved that doesn't require me to draw a resistance network, right? And that's just basically looking at one of these surfaces. So here I'm looking at surface I, and I know that surface I can transfer radiation in general to every other surface, however many there are in the network. So here's surface 1, surface J, all the way to surface N, where N can be any arbitrarily large number of surfaces. Q dot I then is equal to the sum of the heat transfers from node I to every one of these other surfaces, right? So I know how to calculate each of these heat transfers. Now I just have to add them all up. So Q dot I is equal to AI sigma, and then I have the sum from J equals 1 to N of Fij Ti to the 4th minus Tj to the 4th, right? That's basically just saying I'm adding up Q dot I to 1, Q dot I to 2, Q dot I to 3, all the way to Q dot I to N. That's all this does, is it just adds up all the heat transfer rates. So in terms of the equations that I have to solve an N surface problem, there's got to be a whole set of equations. The first one is this equation we just derived, right? This is the net rate of heat transfer to surface I, which is the sum of the heat transfer from I to all of the other ones. And I can write this now for every single surface. So I can write this equation for I equal 1 to N. So this is N equations. And then the other set of equations that I need are a set of boundary conditions, right? So for every single surface, I need to know what's the rate of heat transfer to that surface, or what's its temperature, or at least some relationship between those two quantities, right? So that'll give me N more equations. So together I have 2N equations, and I have 2N unknowns, which are the heat transfer rates and the temperatures. so I can solve my problem. So in doing these problems is going to be done in steps, right? The first step is make sure I know all the areas. That's pretty easy. Make sure I can get all the view factors. That's a little bit harder, but that's, doable. The second step is I'll write all these energy balances, right? And then the third step is now I got to go through and come up with a boundary condition for every single surface. So if I do those steps correctly, when I hit solve, if I'm using ease, or in MATLAB I'd have to put these in some kind of a matrix, but when I hit solve, I'll get a solution, and that solution will give me all of the heat transfer rates and all the temperatures for every single surface in my problem. So we'll illustrate that in a simple 4-surface problem in the next video.